Now that we've talked about the normal distribution and lots of descriptive statistics, we're ready to start making the jump toward inferential statistics, how we can take a small sample, if we do it effectively, if we take a nice random sample, or a representative sample of our population, that we're able to infer from the statistics, the numbers from the sample, about the parameters for the population. And in this section, it's called sampling distributions. We'll talk about that concept in general, but more specifically, we're looking at the sampling distribution for the sample mean, and we're going to see this thing called the central limit theorem, which tells us that sample means are actually, they behave very, very nicely. So first of all, some of this is repetitive from previous sections, but when you have a large population that you want to find information about, the numbers that describe that population, we call those parameters. If you take a smaller sample, the numbers from the sample are called statistics. And if we're looking in particular at some of the things we've talked about, we have certain symbols, usually Greek letters, for parameters. So the population mean is mu, and your sample mean is x bar. Your population standard deviation is sigma. Your sample standard deviation is a lowercase s, usually. Okay? So the idea is, how can I take a sample and use x bar to try to make a really good guess about what mu would be? And we can do that because of this thing called the central limit theorem. It turns out that the sample means behave very nicely, as we're going to see, and we can use probability and things we know about the normal distribution. Okay. So again, you have this picture that I've already described here. You have the population. You're going to take a sample, collect your data from the sample, and try to make inference about the population. And one thing we have to think about here is we have what's called sampling variability. Every time we take a sample, we're probably going to get a different, we could wind up by chance getting the same number, but probably going to get a different sample mean every time. Okay? So we take all these different samples, we get different sample means. Well, what's the actual population mean is the question there. So one way that we can finally make really good inferences about this is think about, well, what happens to all the sample means? If you were to take over and over and over and over lots of samples, or all possible samples of a certain size, how would those sample means behave? One thing we know is the larger the sample, the better off we're going to be, because you're getting closer to the population. So first of all, we call this the law of large numbers. If you take larger samples, then x bar is going to, by default, get closer and closer to mu. And before I can tell you the result, which involves a normal distribution here in a minute, the central limit theorem, first some definitions. Okay, so what we've been thinking at so far in terms of descriptive statistics and the things we've been doing is we've considered our entire set of data, the population, and we've been looking at population distributions, or a distribution of a specific variable. Okay, say we wanted to know the height, the average height of every man in the United States. We would be looking at the population, and our measurements would be the individual heights of individual men. The sampling distribution would be the distribution of all possible sample means. If I took all possible samples of size 20 or some particular size and computed the sample means. Okay? And of course we would have thousands and thousands of those sample means if we did it based on the population of the United States. So if we did that, we'd have all these different sample means. We could look at the distributions of those things, and that's what's called a sampling distribution. Okay? So the big difference here, a population distribution is talking about individuals. A sampling distribution is actually a distribution of a statistic. Okay? It's like the distribution of x bar. And it turns out, I have a GeoGebra app we can look at to see this. Turns out sample means are very nicely behaved. They actually have a normal distribution. Theoretically, they have approximately a normal distribution regardless, as long as you take large enough sample size, regardless of the original population, you'll get an approximately normal distribution for x bar. I have a picture here. I can show you the live applet in a second, but in this picture what I've done is I've created this distribution that's approximately normal. If you look at the black or the gray rectangular type shape, if you look at the histogram in the background there, that's the actual population. And what I've done is taken sample size of 25 and collected sample means. I've had GeoGebra automatically collect a bunch of samples and compute the means, and then plot a histogram of those. And it turns out, a couple of things in the result. It turns out the center is actually going to be at the population mean, which is really nice, and it's a normal distribution. And we can actually talk about the standard deviation as well. It gets divided by square root of n, as we'll see in a minute. But the big result, and it actually doesn't matter what the original population Looks like as long as you take large enough sample sizes, you'll get approximately a normal distribution for sample means. Let me show you the actual applet live here. Looks like my link is dead and I'll have to fix it, but here's my actual GeoGebra file. It doesn't all fit in the screen. I'll have to move it around a little bit. But I have this distribution, and I can take random samples here. We can reset it back. Right now we have no samples and no sample means. Let's do sample size of 20, and I'm going to take a sample mean. Okay. So it took a random sample out of this population, which happens to have a mean of 50.5 and a standard deviation of 29.0. And I got a sample mean of 51.7, which is actually pretty good when you look at it for one single sample. But anyway, that's the value that I got. If I take two samples, that one had a sample mean of 47.8. The mean of the means there, here's where I have that. So if I average these two numbers, I get 49.75, which is now getting really close to 50.5, and I've only done two samples. Let me click the button several times. So now I've taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 samples. I know they're scrolling off the screen a little bit, but I've taken 7 samples and computed the sample means, had GeoGebra do that instantly in the background, plotted those sample means, and you can see already it looks like a perfectly normal distribution there. The mean of the means, so if you were to average these 11 numbers, the mean is 51.95 right now. Theoretically, if you were to take all possible samples of size 20, the mean would be exactly 50.5, and you'd have a nice, approximately normal distribution. So through simulation, this applet allows you to see that. So that's the big idea here that we're getting at. I'll officially put it up as what we call the central limit theorem in a minute. What happens is if your original population is normal, then it doesn't matter what the sample size is. Your sample mean will have a normal distribution. Its mean will be mu, the same as the population. If you average all the sample means, you would get the population mean. Its standard deviation winds up being sigma over square root of n. Right now, with only taking 11 samples out of all the possible ones, I have 6.49's the actual sigma over square root of n, and computed from the data, we got 5.48. So they're getting closer. The more I take, the closer all these things will get together. And so you could do this thousands and thousands and thousands of times, but let me close that out now. I'll try to fix the link to that. Apparently GeoGebra has done some things on their web page and my link doesn't work anymore, but I'll figure that out and get a new link ready for you if you want to take a look at it yourself, just to play around with it.